Hello everyone. In this video, you will learn how to use DDR memory with AXI DMA. You will be shown how to set up the DDR controller in Vivado's block design. After the block design is complete, we will demonstrate a real-time example of DDR memory being used on the FPGA. Alright, let's get started. To start, let's talk about DDR memory and AXI DMA. DDR memory is a dedicated chip on the board that allows for large amounts of data to be stored. DDR is needed in cases where the block RAMs inside the FPGA don't have enough space. A MicroBlaze processor can read from and write to DDR memory with relative ease. The only problem is that it must handle each transfer one at a time. DMA allows the processor to read from or write to DDR without being forced to handle every single transfer itself. It works by having the processor provide a starting address and transfer length. Then the DMA moves the data automatically. So when making a project that uses DDR memory, you need to add the DDR block into the block design. The DDR block is also called the MIG block. MIG stands for Memory Interface Generator. The MIG block is what allows other blocks to read from and write to DDR. To bring in the MIG block, click Window, select Board, and then drag the DDR block into the project. Once this has been done, Vivado will automatically add the MIG block and configure it with the correct DDR settings for the board being used. So on the MIG block, there are 5 main connections that matter for this lesson. The first is the S-AXI bus. This bus allows other AXI blocks, such as the DMA or processor, to access DDR memory. The second is the DDR2 bus. This is the direct connection from the MIG block to the physical DDR memory chip on the board. All you need to do is make this bus external, and Vivado will handle the rest. The third is the system clock I signal. This will be a 200 MHz clock from the clocking wizard. There are 2 reset signals. There's a system reset and a MIG reset. The UI clock signal is the clock generated by the MIG block. This clock is used by the AXI logic that connects to DDR. Now let's look at the AXI DMA block. DMA lets the processor perform multiple DDR transfers without manually handling every individual transfer. For example, if the processor wants the DMA to read 232-bit values at addresses 100 to 300, then the processor sends a start address of 100, a transfer length of 800 bytes, and the command that starts the DMA transfer. After that, the DMA moves the data automatically from DDR to the custom IP block, without the processor being involved. All of the main DMA signals are summarized below. And here's a summary of the last 2 important signals. In this lesson, we are only focusing on reading from DDR memory. Because of that, we will use the following settings when configuring the AXI DMA block. Another block we will use is the AXI clock converter. This IP block allows an AXI bus to cross from one clock domain into another. We will use this block to allow AXI buses running on the system clock to feed into IP blocks running on the MIG clock. The next block we will use is the AXI SmartConnect. This block is used when multiple AXI blocks need to connect to the same destination. In this design, both the processor and the DMA need to access DDR memory. Because of that, the SmartConnect allows both AXI paths to connect into the MIG block. You can think of it like a multiplexer, but for AXI buses. The next block we will use is the processor system reset block. This block creates reset signals that are synchronized to a specific clock. In this design, we will use this block to make reset signals that are synchronized for both the system clock and the MIG clock. This is the receiver IP from the previous lesson. All it does is receive an AXI for stream transfer and let us use the switches and LEDs to check if the correct values were received. So this here is the overall block diagram for this project. Using DDR is very easy after the block diagram is set up, but setting up the block diagram itself can be very tedious. To help with that, I will show you how to set up the entire project from start to finish. Start by making a new project. Give your project a name. Add in the constraint file. Then search for the board. I'm using the Nexus 4 DDR board, so that is the one that I must choose. It's important that you select the board file and not the part manually, because the board file helps Vivado automatically set up the MIG block. Now create a new block diagram. Add in the MicroBlaze processor. Add in the clock wizard and make there be two output clocks. One output will be 100 MHz and the other will be 200 MHz. Also remove the signals that are not needed. Now run both block and connection automation. Now to get the AXI interconnect into the design, let's add the DMA block in and rerun automation. Now let's disconnect the DMA block. Now let's configure the settings for the DMA block. Now to add in the receiver IP block, we must repackage it again. If you have been following along the previous videos, you should already have the IP ready to package. Now you must add in the MIG block. To do this, click Window, then Boards, and drag in the DDR block. Now remove the connections that were automatically made. For now, we just want the block by itself. Now add in the AXI SmartConnect Block. Now let's rearrange the blocks to match the overall block diagram from before. Now let's add in 2 clock converter blocks. Now let's add in the processor system reset block. Now let's add in a constant and get the overall block design ready. The block design is now ready. All that is left is to make the connections. Since there are a lot of signals, I will show you how to connect all of them. I recommend making the connections in your own project as you watch this video. So first, let's make the LEDs and switches external and make them match the names from the constraint file. The DDR bus does not need to be renamed after it's made external again. We also need to rename the clock to match the name from the constraint file. Now I will make the connections. Follow along closely because there are a lot of signals. All of the connections have been made. Now let's validate the design to confirm that it's correct. Now let's add in the constraint file. Now let's generate an HDL wrapper and generate the bit stream. The bitstream failed because I accidentally connected the 100 MHz clock to the system clock input of the MIG block. To fix this, we must just connect it to the 200 MHz clock. Now let's regenerate the HDL wrapper and regenerate the bitstream. After the bitstream is generated, you must export the hardware, program the device, and set up the Vitis project. I will not show those steps since they have already been covered many times in previous lessons. Once you have set up Vitis, just copy in the provided demonstration code and run it to see the demonstration in action. If you are encountering any problems, it's probably because your Vivado IDE assigned different addresses to each hardware block. To find out what addresses were actually used, navigate to the X parameters file. The X parameters file can be found here. This file will tell you all of the information you need to know. So when we run our code in Vitis, the processor will manually write 16 values into DDR memory. Then, the processor will configure the DMA by giving it the DDR starting address, the transfer length, and the command to start the transfer. After that, the DMA will move those 16 values from DDR into the receiver IP block. Once the code is finished running, we can flip the switches and observe the LEDs to check if the entire system worked correctly. If the correct values appear on the LEDs, then we know that the DDR-to-stream transfer worked as intended. So this here is the real-time demonstration after programming it. As you can clearly see, all 16 numbers that were written into DDR memory were successfully transferred into the receiver IP block with DMA. I recommend running the code yourself and changing the 16 values so that you can see it working with other numbers. Alright, that's all for this video. Looking forward to seeing you in the next one.